So, anytime you start working on these projects, IoT projects, if you're playing around with stuff, you end up playing with a servo just because they're cool. But one of the problems I always had was like knowing where the servo's at any given time. I can send it somewhere, but if I power on, I don't know where it is. Or if I were to turn it off and it gets manipulated by something, maybe I want to use it anyway. The other thing is if you wanted to slow down before you got somewhere, I'm going to go from 0 to 180, but my arm's pretty long, so I'm going to slow down as I get closer to that. Like, how would you do that? And how would you know where it actually ends up? And so one of the ways to do that is to get analog feedback on a servo. And it turns out that you can buy feedback-based servos, and I recommend that as the approach. But if you're like me and you got a pile of really cheap servos lying around, or even some spares, and you want to do your own thing, because that's how we get into this, then what we can do is we can actually add a feedback loop wire on these. And you got to be a little cautious with this. It's not going to be 100% accurate, and the servos are noisy, and don't expect it to be, brain surgery level of accuracy on it. But it's pretty interesting to play with, and you probably can work it in. So the way this works is inside inside the servo kind of has to know where it got to, right? And where it's at, and it's part of the feedback loop, and you do this pulse train. The pulse train moves it, but if the pulses are still coming, how does it know where to stop? And the answer is it kind of compares probably some voltage internally built by the pulse train against the voltage that it actually sees across the potentiometer. So basically the idea here is you have a servo with an arm on it, and in one position, let's call it 0 degrees, you're going to be at one end of this potentiometer, and so you'll have some voltage. And it turns out on mine that's pretty close to, well, the one end is all the way maxed out, and the other was somewhere in the middle. So every one of these is going to be a little different, and I took mine apart just to see how it worked, and so I may not have put it back together right. But the idea is, if the range is 0 to 180, as shown here, there'll also be a midpoint in the middle that's like 90 degrees. That will actually have the mid voltage. So if it went from 1/10 of a volt to 3 volt, or 1 volt to 3 volts, then the midpoint would be 2 volts, right? You don't necessarily know that it's centered from 0 to 3, but you know that the midpoint's going to be some voltage halfway between the one end and halfway between the other, right? And so that's kind of cool. And the question is, can we pick up that voltage and then look at it? And it turns out there's some examples on the net, but I didn't like any of them, of course. So I went, it turns out it's super easy. And again, I'm using the 9-gram, super cheap, but I really like them, plastic. It's got a little bit of metal gearing in it, but it's mostly plastic gearing. And in this case, I've got it hooked up to a Seed Studio. I don't know how you pronounce XIAO. Zao. And that thing is an ESP32 C3, and it's only got like 11 I/O pins on it. But if I only need one for the servo, and I need one for the feedback loop, right? So super simple hookup. If I can figure out how to add a wire inside this servo that will bring out this potentiometer voltage, and then I can use it. And then I kind of got to be high impedance, right? Because I don't want to be sucking down that voltage, because I'll actually crash the servo. We don't want to do that. We want to be a vampire that doesn't kill. You know what? Never mind. So I have this simple program out there on this repo, and basically what it does is it moves from 0 to 180 degrees in 30-degree increments, and then it rolls back to 0 again, all in one sweep. And so I just wanted to prove to myself that it worked. And so this sample program, check sweep, it says we're moving to 0. It's 600 microsecond pulse train. This was for some other stuff. It converted the pulse train microseconds into a duty cycle on a duty stepping on the timer, which is a different talk. And what we can see when this is done is that has a voltage on a 65K scale. This isn't a voltage. This is actually like a proportion, right? So on a 65K scale, it's got a 9,600. So the 0 position is 9,600. And if we scroll down here, we can see that the 180 position is full range, right? So I'm probably losing a little sensitivity at the high end, and the bottom end didn't come out quite where I expected, but I can probably go play with a bunch of these servos and see. I haven't compared them, see if they're all the same. I need to add wires to more. But basically you can see here that we're sitting at 9,600 in the 0 position. At the 90th degree, we're sitting at 37,513. You double that, that's like 64, 65, 26 or something. So that's almost dead even, right? Halfway between the 96.18 and the 65K, the 90 degree. So we know we have pretty good range. If we've calibrated our software so that 0 degrees has an ADC range setting of 96.18, and I don't really care what the voltage is, right? What I really care is proportional. What does this thing look like? What's the min? What's the max? And then how many steps have I got in between? This thing's a 16-bit ADC, so I can end up with 64K worth of steps. And so that gives me pretty good accuracy. If I'm on an ESP32 C3, I'm looking at 1,024 steps, so a lot less accuracy across that range, right? Now, that'll be way more accurate. And it turns out a servo on 10-bit steppers or 10-bit control in the PWM probably isn't going to get the accuracy we want anyway. So one nice thing on these ESP32 is we have more fake precision to work with. So how did I do this? Basically, I feel like these have all been produced the same way. If you look at this thing, can I do that? Yeah. If you look at this thing, it's basically got 4 screws on the bottom that have been pulled out, and it's a 3-part case. The gearing's in the top, the motor and the potentiometer and control board are in the bottom, and then there's a little cover with a slot cut in it where all the wiring sticks up inside of this thing. So basically what we need to do is we open the 4 screws, pull the bottom off, looking in from the bottom on these micro servos. We have the 3 wires for the input, the 2 motor wires, a chip that does kind of like the timing management for this to generate the pulse train, read the pulse trains and convert that into motion control. And then it turns out there's a potentiometer that the gear train runs through that I showed up above, right? That the wiper goes back and forth based on where the arm is. And it turns out that thing on these little ones, unlike the big heavy duty ones, it's soldered right to the board. So we can totally get to it, right? So one of these is going to be going to be 3 volts or 5 volts, depending on whatever you power this thing with. And one of them is going to be 0 volts, and the other is going to represent the arm position in that range that we had above, in the range I had up here. So in a range from 96.18 to 65.535, I will know the arm position in one of the across that range on this little dot here. So what we need to do is solder a wire to this middle of this potentiometer, and super easy. Well, not super easy. It's pretty easy. I would just cut the wire short, tin it, make sure you got a little bit of solder on it. Just tap this solder blob and this wire at the same time. They will merge the solder between the 2 of those, and we'll have a wire. Super easy. And then it'll kind of look like this guy, right, when you're done. So we have the bottom off of this thing. You can see the top 2/3 of this, and then we've got the sensing wire coming out. So what's the hard part there? Well, if you look at it, man, we got to figure out, somehow we want to get the wire out, and this slot is just a little narrower than those wires so that it acts as a strain relief so that the wires don't get ripped out of the servo. So what are we going to do? We're going to add to this slot or make a new slot, right? And what I did is I took a metal file and I just made a spot for an extra wire, but a little smaller than the wire so that when the whole thing gets bolted together, it's still snug, right? So you could create a whole extra slot for this. It's probably a pretty good idea. I just have a little triangular file. I filed it down, right? And then when you put the whole thing back together, and you end up with something like this. So I took a jumper wire that already had a socket in it so it would match these guys, cut one end off, ran it in there, did that little bit of notchy thing on the end of this, and the end result was something that looked like this that I plugged in, right? And I think that's all the picture I got. Yeah. So the sample code's super straightforward. I actually used the repo that I've already got and created a test program. There's one out there called Check Sweep, I think it's called, in this repo so that you didn't have to run everything. Yeah, from Check Sweep. So you can actually run this thing in the REPL with no other thing. You can from Check Sweep. Oh, there's an error. I will fix that. No parentheses there, baby. And then you just type sweep ESP32 open close, and it will exercise this servo on pin 5, assuming, like on the ESP32, you're pretty restricted on what your ADC pins are, although on the 8266, you've only got one. So I picked pin 4 for the inbound read off the potentiometer, and I picked 5 for the servo. And this is where I got these. I don't make any money off of those. I'm just telling you what I'm using for the driver for this. And I hope that's useful and that you can play with adding feedback or reading the position from your servo to your application. Have a great day.